Welcome to the Explainer. If you've ever stared at a massive block of Java code and felt just a little bit overwhelmed by the structure, well, you are in exactly the right place. Today, we're taking what are usually taught as incredibly dry, textbook Java concepts and transforming them into a highly practical, genuinely powerful developer's toolkit. We aren't just memorizing terms here. We are going to understand exactly how Java OOP concepts work under the hood so you can build some truly bulletproof software.
Okay, let's dive straight into this. 1. The Java OOP foundation. 2. Encapsulation. 3. Inheritance. 4. Polymorphism. 5. Abstraction. And finally, 6. The interview cheat sheet.
So let's start with our foundational thesis. Java is fundamentally based on object-oriented programming, or OOP. Honestly, if you want to write Java, you literally have to think in objects. Understanding how these OOP concepts work isn't just some nice-to-have bonus skill, it's the absolute bedrock of everything you will ever do in this language. It's how you organize your logic, how you protect your data, and how you build applications that can actually scale up without completely breaking apart.
Section 2. Encapsulation. Protecting your data. Think of this first pillar as the vault. It's a security system locking down your foundational code. Encapsulation literally means wrapping data, so your variables, and your methods into a single unit, a class, and restricting direct access to that data using access modifiers. Just imagine a standard capsule pill. Everything you need is safely contained right inside that shell. In Java, encapsulation is all about keeping your data safe and totally self-contained. You don't let outside code just reach in and mess with your variables directly. No way. You force them to go through the approved channels. To really picture this, imagine you've got a student class, and inside it you declare a private string for their name. That private keyword? It's basically the bouncer standing at the door of your data vault. Because it's private, no other class can just change a student's name on a whim. If they want to interact with that name data, they have to use your approved methods, specifically the getters and setters that you, the developer, maintain complete control over.
And why does this matter so much? Well, this isn't just theory. This is exactly how you prevent malicious or even just accidental access to your variables. Encapsulation protects data, greatly improves your security, and it makes code so much easier to maintain. Because think about it, if you ever need to change how a name is formatted, you only have to change it right there inside the student class, not in the 100 other random places in your app that might be trying to access it.
Section 3. Inheritance, reusing your code.
If encapsulation was the vault, inheritance is the blueprint for rapid expansion. Inheritance allows one class to acquire the properties and methods of another class using the extends keyword. Basically, it's a built-in mechanism to stop you from writing the exact same code over and over again. If you have a general category of something, and then a much more specific version of that thing, the specific version can just inherit all the traits from the parent class automatically, no extra typing required.
Ah yes, the classic dog extends animal scenario. Look, it's the undisputed heavyweight champion of all programming tutorials for a reason. It works perfectly. Say animal is our parent class, and it already has methods for eating and sleeping. By saying class dog extends animal, our new dog class instantly knows exactly how to eat and sleep. But we can also add a highly specific behavior, like a bark method, that is entirely unique to the dog.
The crucial point here is that inheritance gives you massive code reusability and seriously reduces duplication. If you spot a bug in the parent class and fix it, boom, it instantly fixes it in all the child classes that inherit from it. It's a total game changer for developers who are building out really complex systems.
Section 4. Polymorphism, flexibility in action.
I absolutely love calling this one the shapeshifter of the developer toolkit because it allows your code to adapt dynamically based on whatever situation it's in. Polymorphism translates to many forms. In Java OOP, it just means one interface, many forms. It's a short, punchy little definition, but it hides an incredibly powerful concept. And what's really fascinating is that this single concept actually comes in two very distinct flavors, depending on when the shapeshifting happens.
You have a very clear distinction between compile time and runtime polymorphism. At compile time, you've got method overloading. This is when you have multiple methods in the exact same class with the exact same name, but different parameters, like a calculator with one add method for 2 numbers and a separate add method for 3 numbers. The compiler knows exactly which one to pick. But runtime polymorphism? That's method overriding. This is when a child class provides its own specific implementation for a method that was already provided by its parent class.
For example, say you declare a new object of type animal, but you actually instantiate it as a new dog. When you call the sound method on it, it doesn't just print some generic animal sound. It specifically outputs dog barks. That is the pure magic of overriding. Even though the reference is just a generic animal, the Java virtual machine dynamically figures out at runtime that, hey, it's actually dealing with a dog and executes the dog's specific behavior.
So how does this actually help you in practice?
It gives you ultimate flexibility and makes code extension incredibly smooth. Imagine writing a program that has to process hundreds of different types of animals. Thanks to polymorphism, you don't need a massive wall of 100 different if statements checking what animal it is. You literally just loop through a list of animals, call the sound method, and let polymorphism guarantee that each specific animal makes its correct sound automatically.
Section 5. Abstraction. Hiding the details.
Think of abstraction as the dashboard. It simplifies an incredibly complex system underneath. Abstraction means showing only the essential details to the user while completely hiding the background implementation using abstract classes or interfaces. Think about driving your car. You know that turning the key or hitting a button starts the engine. You absolutely do not need to know how the fuel injector mixes air and gasoline to make the car move, right? Abstraction hides all that messy, complicated logic under the hood and only shows you what you need to see to operate it.
If we were to code that out, we'd create an abstract vehicle class with an abstract start method. But notice, there wouldn't actually be any code inside that start method. It's just a declaration. This abstract class essentially forces any child class, like a car, to have a start method, but it leaves it entirely up to the car to define exactly how it starts. Maybe a car starts with a key, but a motorcycle starts with a kick pedal. The vehicle class doesn't care how it's done, only that it gets done.
The core benefits here are incredibly clear. Abstraction hides implementation details and exposes only essential functionality. When you are working on a massive codebase with dozens of other developers, this is exactly how you keep things manageable. You just give them a clean dashboard, an interface to interact with, and you hide all your complex, moving parts securely away.
Section 6. The Interview Cheat Sheet. All right, let's ramp up the energy and lock this in. This is your highly actionable rapid-fire study guide to help you crush your next coding interview. Encapsulation? It hides data using private variables, accessed via getters and setters. Inheritance? Reuses code from another class using the extends keyword. Polymorphism? One method, many behaviors, achieved through overloading and overriding. And abstraction? It hides implementation details using the abstract or interface keywords. Whenever you get stuck, just mentally return to this exact summary.
So we've unpacked the vault, the blueprint, the shapeshifter, and the dashboard. You now have a really solid understanding of exactly how Java OOP concepts work. I want to leave you with a question to chew on. As you boot up your IDE today, which of the 4 OOP pillars is the most crucial for your next project? Think about how you can immediately apply this toolkit to write cleaner, safer, and much more flexible code. Thank you so much for hanging out with me on this explainer, and happy coding!